Hello, this is our second video on Simulink. Last time we saw how to solve some problems, right? And use basic blocks. For example, we solved the drag problem for projectile and the nonlinear pendulum, and we learned a bunch of things. Now here is time to learn about other blocks and some more advanced topics. So let's get started. So here is the first file I made for you, and I want to show you a few other blocks that might be interesting to you, especially under Simulink under dashboard. So what I have here is the ramp block, and ramp, basically the output of it is the time, really. So the function is f of t equal t. Now you can change the slope of it, so you can make it like n times t. And if you want, you can give it a delay, so then it is not going to start at time 0 or initial output, okay? So you can give it a y shift here or an x shift here and change the slope, right? So then here I have multiplied by some gain, but this gain is not a regular gain. This gain is actually what I want to change during the simulation. So, and I'm not going to double click on this each time and type a new number. Instead, I use a slider element that allows me to change the value of this gain by just moving this slider on the bar. And so the output of here is going to be basically times t times some number k. So it's going to be k times t, correct? So if I want to write it, it's going to be t, and this is going to be k times t. And then you send it to the sine wave function. Now, sine wave, there are two scenarios for it. Either the sine wave generates the time itself based on the simulation time. So if you go to it, the sine function has a bunch of parameters, and the time for it is either the simulation time, which if you use, then it doesn't need any input. So it just generates the sine function for you. And there is amplitude in it. You can change bias, frequency, phase. You know about the sample time. So sample time is nothing new. But let me very fast mention what is amplitude, bias, frequency, and phase. And also I mentioned these three numbers one more time: slope, start time, and initial output. So you know mathematically what they are doing. So for the ramp function, as I said, your function in general might not start at time 0, might start at some time other than 0. And the initial value of it might not be 0, it might be something. And then it has some specific slope. Okay, so this is your initial y. This is your initial time. And the slope of this line, if you call this angle alpha, then tangent of alpha is the slope. Okay, so this is for your ramp input. And for the sine function, a sine function in general can be written as a times sine of omega t plus phi and then plus b, where here this a is the amplitude of the signal. It shows how much the signal is going up and down, right? It determines the range of the signal. Then this omega is called the frequency of the signal. The unit for it is radians per second, not hertz. If you want the frequency in hertz, remember that the frequency in hertz means the frequency in radians per second divided by 2 pi. And the frequency in hertz is also equal to 1 over period of the function. So if anybody ever gives you the period of the sine function or the frequency of the sine function in hertz, this number that you provide in the block as frequency, you have to, if it's in hertz, you multiply it by 2 pi to get it. If it's t, you have to do what? You have to say 2 pi over t. So from here, if you want, again, if I give you frequency f in hertz, you have to multiply it by 2 pi to get the omega and enter it in the block. If I give you what? If I give you t, then you can plug it in 2 pi over t and get your omega, okay? So depending on what you have, remember that the number that you enter inside that block is always radians per second. And then you have phase shift phi. So this is phase, or people call it phase shift. And it determines the initial value of the function and the amount of shift along the x-axis. And this b is called bias, and this is the amount of average of the signal. So you know the sine function goes from negative a to positive a if magnitude is a or amplitude is a, if there is no b. But if there is a b, a constant value added to the signal, then the average of the signal is going to be b units instead of 0. So you're going to shift it up b units, okay? So I can show you those stuff here. So let's say you have the sine function, and to make life a little bit better for you, I will move the average of the signal up. So this is t, this is that f of t, and of course these guys have to be all at the same level. So let's say something like that. So right now, if you look at the average of the signal, the average is here. Which means the max plus mean divided by 2, okay? This average signal is B, bias. Then you have amplitude, which is basically from the bias to the peak or to the min, okay? Any of these two values are A, amplitude. So your max is B plus A, your min is B minus A. And then this initial value here is determined by phi. This value is B plus A times sine of phi. So if you know B and A, it's phi that determines the amount of the initial point. Okay, and the bigger, the smaller it is, this sine function's initial point will go up and down. So your sine function moves a little bit to the left or right. And then this here, from here to here, is a period of the signal. So if you divide 2 pi by t, you will get omega of the signal. The bigger the omega, the faster the sine function changes, okay? So this is a very short background about what we are doing here. And now, what I'm doing, instead of getting the time that this sine function needs from the simulation, I'm going to provide it to it. So in the meanwhile, I can multiply it by a gain k. So since I put my frequency at 1, amplitude at 1, bias and phase at 0, my signal here is simply sine of whatever comes in, okay, times t. So it's k times t. So this is going to be sine of k times t. Therefore, k here, this gain for me acts as what? As the frequency omega. So the bigger I make this k, I expect my sine function to change faster and faster. And then I connect it to a scope block that I can visualize. But as I said, the goal of me is not to go each time, double click on K, change it, and then look at this scope block and see if the signal has been made faster or slower. What I want is, without double clicking on this scope or the gain, I want to be able to move the K in real time and see the effect of K on the output again without double clicking on this scope block. So I want to see it on this outside window. that is always open. I don't need to double click on it to open it. This window here is another scope block, which we call dashboard scope, and this is always open and you can always look at it. So I'll show you how to get these two blocks, but the rest of it is relatively easy, right? So if you go under library, under sources, you can see the sine function. That's this guy. Gain is clear. The ramp function is also under sources. Scope, you know it. So now where is the dashboard and where is the gain? So here we have a set of blocks that I really like. They are under dashboard, and here there are a bunch of different things that you might like. For example, this is that slider that you can see here, okay? Or you can have toggle switches, radio buttons, rocker switch. There are so many things, gauges, push button, linear gauge, light. I'll show you. These are really cool stuff that you can add to your Simulink and make it look a lot nicer. And then you can have, this is the dashboard scope. That is this guy, okay? If you want, you can just click anywhere and just type in dashboard scope, and it will bring that guy that you just saw, okay? So when you bring, let me bring them here and show you. So I have this guy here, and then I go here under dashboard, bring a dashboard scope, and set it up here, and then bring a slider. So when you bring these guys, you have to connect them to the blocks in the Simulink. So if you double click on this to connect it, it says which gain, which block do you want this slider to change? And you say, well, I want this gain. So you double click on the gain and you say, okay, now whenever you move the slider, I'm going to change the value of that gain. And you say, okay, connect it to it for me. And it says, which range do you want me to change? And I say, any frequency between 1 to 10, I want you to change, okay? And you say, okay, and okay that. So now this is anywhere from 1 to 10. And now by double clicking here, you can change the value of that gain, take it anywhere that you want. Now here you want to show the signal that is going to scope on this dashboard scope, which you don't need to double click every time and open. So you double click here, says, okay, which signal do you want me to show? And you double click on this signal, sine of kt. So show it to me, and then you provide values for y-axis from negative something to something, right? Let's say here I want to go from negative 2 to 2, knowing that the amplitude is 1 and there is no bias, and that should be good to go. And then I am going to simulate this. So right now the frequency, let's set it at, let's say 2. So this is going to be sine of 2t. Right? And then if you want, you can move this guy and make it like sine of 60. You see, it's changing faster. You can make it sine of 10t. It should be even faster, right? And you can always maximize this in size so you can see better. So clearly see the change in frequency, right? And now let me bring it back and do it. So you can see the effect here without closing and opening something, but you might wonder, well, because this is going very fast, so before I'm able to double click on this guy and change the frequency, that 40-second simulation is gone. So when I change it, I have to rerun it to see the effect. And you might wonder, could you slow it down so that it doesn't go all the way to 40 seconds? And while this sine function is moving on, you can change the frequency and see the effect all in one graph, not in several graphs that are one overwriting the previous one. And the answer is yes. For that, you need to look at this guy called step back. And here you say enable step backing, and it says, okay, how many steps do you want to go backward or forward? Say, let's say 10 steps, and you okay that. So now look, when I click on run, okay, now if I want, I can go on step forward, and it's not going to go all the way to 40. So each time I can only go 10 steps here. You see, I'm not going all the way from 0 to 40, and this is using frequency of 2.2. Now, before I go to next step, I change the frequency to something bigger, and now step forward. And look now. You see, now the signal is getting faster. And now I go to maybe 8, and again do it. And you see it's even faster, right? So this step forward, step backward, and if you want to continue, it goes all the way to the end. And if we want at any point, you can stop it. So this step backward, forward, and continue, and these dashboard elements are some amazing things that can make your Simulink a lot better. Okay, so this is our second demo here. Now let's go to more and more demos, and I'll show you nicer stuff. So that's about it. Now we go to demo number 2, and here I want to show you some logics, how to do logics. So one of the first blocks that I mentioned, and it's very powerful block, is called switch. So this is the switch, block, and what switch does is you provide some condition and some threshold. Okay, so you say, I want the signal in the middle to be bigger than 10. And you pass to it a signal in the middle. Now, if the signal in the middle, the number that is coming in is bigger than 10, which means the condition is true, it passes what? The signal that goes to the top input port. So the output is going to be what? Constant 0. But whenever this condition is not valid, it's violated, it's false, it passes which input? The input at the bottom port, right? So when the condition is true, the top port, top signal passes through. When the condition is false, the bottom signal passes through, right? This is called the switch block, and you can find it in library under signal routing at the bottom here. So this is really a switch block, and here I'm passing the time to the switch, and this time goes from 0 to 30. So when you are between 0 to 10, right, which is this condition is false, the value of the signal is going to be 1. After 10 all the way to 30, this condition is true, so you're going to get a 0. So what you will see is a step behavior. In the first 10 seconds, the output is 1. In the next 20 seconds, the output is going to be 0. Okay, so let me first run it and show you, and then we talk about other stuff. So here we go, and now you can see the scope block, right? So the first 10 seconds is 1. After that, it is what? 0. Now, if you don't want it to be 1, you can change it. You say, well, in the first 10 seconds, I want it to be 2, but after that, I want it to be -1. Okay, it's up to you how much you want the signal to change, between what number to what number, or what signal to what signal, and you clearly can see that, right? Or again, if you don't like it, you say, for example, here in the first 10 seconds, I want the signal to be like a sine function, but after that, I want the signal to be like another function, right? So let me show you that. So you can go under inputs or sources, and first say it's a constant, but after that, I want it, let's say, to be what? A chirp signal. Okay? Right? So, and what is chirp? Chirp is a signal that is like a sine function, but the frequency of it is increasing. Right? So your frequency at the target time of 100 seconds will go to 1. Initially is 0.1. Now let's say I want it to start at 1 and end up with 10, and I want it to happen in 30 seconds, right? Or in 20 seconds. So this is like a sine function with increasing frequency, and this is what you hear in ambulance and firefighting machines and so on when they turn their siren on. Okay, it's mostly a chirp signal, but here we go. Now, if you can see it clearly, you see that first you have the chirp signal, and then you have the constant. Now, I should have said in the first 10 seconds, because The bottom one is for when the signal condition is not valid. And if you want, since this signal is fast moving, I would change my sample time to a big number so that you can see its variation better. Okay, so now you can see it that in the first 10 seconds the chirp signal is in. After that you get to -1, and you clearly see this is a sine function with increasing frequency. Okay, it's called chirp signal. Now, another thing I have in all of these demos is this guy called subsystem. What is a subsystem? So if you go down here in Simulink, and then you have this part here says ports and subsystems, you can bring a subsystem here. And what is a subsystem? I'll tell you. So first let me show you where to find it, and that's here. And what does it do? So a subsystem is like a mask. It's like putting a bunch of blocks that you want inside a folder. It's like a folder, and this folder, this system, can have a bunch of input ports and a bunch of what? Output ports. Okay, it's a system, but it's not the whole part of your Simulink model. It's just a portion of it. Okay, so let's say, for example, if I want to have a DC motor or anything, right? Then you know the DC motor has basically an electric component or circuit, and it has what? A mechanical part, right? The electrical part, you pass to it a voltage, and then it has basically this current that goes in, and then this current is transferred into torque, where torque is a constant times the current. And then this torque that is applied to the motor shaft is going to give you the angle or angular velocity of the shaft, like let's say omega. So this is the mechanical subsystem for the motor. And this is what? This is the electrical subsystem. So instead of putting all of those blocks inside each one and making the Simulink model very crowded, very busy, that you cannot see what is what, I would put each category of them that belong to the same subcategory, I put them in a subsystem, and it makes my Simulink model a lot more organized. Okay, another example of that you can see here in this backhoe model that I'm going to talk about in a minute. But here you see there is a backhoe model, and this backhoe model here is a subsystem. It's called plant, whatever. You double click on it and you go inside, and you see now this vehicle has different components, subsystems. One of it is the vehicle, the other one is the mounting assembly, the other one is the backhoe arm. Then you have some hydraulic system, right, and so on. And then you also, outside, you have a controller, you have sensors, actuators, and so on and so forth. Okay, so by putting stuff inside, and each one of them, when you click on them, there is a ton of other stuff in it. So the upper vehicle is a subsystem for itself. The lower vehicle is a subsystem. Now here they are under mask, so you cannot see what's inside them unless you right click on them and say mask and then look under the mask. Then you see there are lots of blocks, and again each one of them could have further subsystems, right? So imagine each one of these with all of these blocks in them, right? You want to bring all of them and put them all in this front page. Well, that is going to be huge. Okay, you cannot see what is what. But here you are organizing stuff, correct? So the subsystem is always a very good solution to keep your model organized. So what I did here, this switch system is a subsystem for me with one input, which is time, and one output, which is output of the switch. So I put my blocks in this subsystem. And again, a subsystem does not need to have one input, one output. You can add as many as inputs and outputs you want. So here, let's say I have one more input, another more input. So this system has 3 inputs, and then what? Let's say it has 2 outputs. Here we go. So now if you go out, you see it has 3 ports for 3 inputs, 2 ports for 2 outputs. Okay, and you can put whatever you want inside it and then bring the inputs and outputs. Okay, so this subsystem is a very, very good idea for organizing. So that was the switch. Now I want to show you more logics. So here is another logic here. And again, I'm passing the time as the input to the system. Now, what am I doing here? Here, I'm doing logical operator AND. If you click on this guy, you can change it from AND to OR to XOR to NOR, NOT, and so on and so forth. And you can have as many input signals as you want, so you don't need to necessarily say A and B. You can say A and B and C or D or whatever like that. And what I'm saying is this. I say this time comes here and then be compared against 10 and against 20. If it's bigger than 10 and if it's less than 20, so it's between 10 and 20, AND them and then send the output out. So this output is going to be number 1, true, in other words, true, if what? If this time is both what? Bigger than 10 and at the same time what? Less than 20. As long as the time is between 10 and 20, the AND of both of these truths is going to be true again, so the output is going to be 1, right? But if it's less than 10 or bigger than 20, one of them is false, so when you AND it, the output is false. So you're going to get a 0, right? So if you look here, you see, less than 10, bigger than 20, the output is 0. Between 10 to 20, the output is what? 1. So here I'm doing comparison against constants, and then I'm doing logical operations to combine them. And you can find comparisons and logical operations here. If you go to logic and bit operations, here you have comparison against constant and 0, and here you have logical operation and in general relational operations. Okay, right? Because if you look at this, you can change this operator and you can change the constant, right? And that relational operator is also another general case that you can provide a little bit more operations like is nan, is finite, is infinity, and so on, right? So this is another logic that I wanted you to see. The other one is, can I do something like if else in Simulink? Sure. So look at what I'm doing here. I'm using 2 switch blocks because each switch only can consider 2 conditions, A or B. So if I want to say if else, now I have more than 2 conditions to check. Therefore, I have to use more than 1 switch block. So here I'm using 2. So what is it here that I'm doing? I'm sending the time to these 2 switch blocks and comparing the time against 10 and 20. Now, if the time is bigger than 10, then the output is going to be 1 for this guy. Okay. What about this one? Well, it depends. When you say bigger than 10, is it also bigger than 20? Or it's between 10 and 20? So if it's less than 10, let's say, if it's just less than 10, then both of these conditions are false. So what it will pass through is the bottom signal for both. So the result is going to be 0 and 1, and you add them together, so the output is 1, right? So as long as the time is less than 10, the output is 0 plus 1. When it's between 10 and 20, now this one is false, that one is true. So the output is going to be 1 plus 1. So the output is going to be 2 instead of 1. And when it goes over 20, now both of them are true, so the output is going to be what? 1 plus negative 4, which is negative 3. So your output is going to be 1, then it's going to be 2, then it jumps down to negative 3, and you can see that here, right? So I have 3 outputs for 3 different ranges, between 0 to 10, 10 to 20, and 20 to 30, thanks to combining 2 switches. And I can do here AND of them, I can add them, I can do anything I want as long as I know what constant values to use here. I can get the proper outputs that I want in this scope block. So this is doing if else using combination of switch blocks. Now you might say, is there any other way that I can do it? And the answer is yes, sure. This time, instead of all this wiring and stuff, I put all of that in the code, because Simulink is really good for connecting blocks and everything, but sometimes maybe if I want to create something like a for loop, a while loop, if else, and other of those what we call logic flow controls, it's better that we directly code them instead of connecting blocks to make them happen. So what I will do here, I'm going to bring a MATLAB user-defined function, okay? And inside this guy, if I double click, it allows me to write my code as a function. So if you look here, I have a function, and in this function, the input is u, the output is y. And I say if u is less than or equal 10, the output is 2. Else if it's bigger than 10, less than 20, then it's -3. Otherwise, if it's bigger than 20, the output is what? 5. So here you go, 2, then -3, then 5, right? Or if you want it the same as the previous case, you make this one 1, you make this one 2, you make this one -3, correct? And so you see, I have my if-else if inside this function, and this function is an internal function. So in addition to your Simulink model, in the folder that you have saved it, you're not going to see a separate M file called Fcn. This is an internally saved function. It's not external. So this function is saved inside the Simulink model, not outside as a separate M file. Now, where can you find this MATLAB function? Again, you have to go under Simulinks and go here to user-defined functions. There are all sorts of functions here. Some of them are quite a bit advanced, like S functions. Right now, what I want you to consider is just this one for initializing your programming in Simulink with user-defined functions. I say you better start with MATLAB functions. Don't go for these more difficult ones for the moment. So MATLAB function is a very good one, and you can bring it. And now here, if you look, if I run this and look at the output of this, should be the same as the other one. You see? But instead of all of those wires, I have what? I have my function written as a code. Now you might say, is there a chance that this MATLAB function can have more than one input or more than one output? Because here you have one u and one y. Could you change this such that this MATLAB function that you write as an M file, it has more than one input, one output? And the answer is yes. All you need is you double click here, and instead of saying function y, you say, for example, it's y1 and y2. I have two outputs, and this is the function of, and then you say, let's say u1 and u2 and u what? 3. So I have 3 inputs and 2 outputs. So now if you save it and get out, you see, now your function can have 3 inputs and 2 outputs. So you can modify it to your own needs. Okay, so here is some logic that you can do in Simulink. Right, so that's demo number 2. Now I have some more stuff to show you. Demo number, let me jump to 4, then I come back to 3. Here is if you want to read and write from files, because you learned that you can read and write from workspace, but what about other types of memories and files? Can I do that? Yes. So here, let's say I want to read something from an Excel file and use it as the frequency of my signal. And then the result of that, which is sine of that number times t, is an array. I want to write it to what kind of file here? To a mat file, okay? Right? So here, I'm not going to do anything with workspace. I'm going from an Excel file to a mat file. Can I do it? Sure. Well, what I need is I go under Simulink, and then I go under sinks or sources. If I go to sources, I have from spreadsheet, which is what I'm using here. I can read it from a mat file. I can bring it from workspace and so on. And the same thing with sinks. I can write it to workspace. I can write it to a mat file and so on. So here, I provide the name of the Excel file, I provide the sheet number, and I provide the range that the data is in. So it's in sheet 1 in a file called frequency, and it is in cell number A2, and I provide a sample time. So the number here comes in is F. The number coming out of this RAM function is T. So the output is going to be F times T, correct? Yes, and then this is going to be what? Sine of F times T. So F is going to be the frequency of your signal. Okay, and you know, I told you, you can double click on any wire and type whatever you want as the name of that signal. And the result going to go where? If I double click here, the result is going to go to a mat file called result.mat. The name I provide for that variable is X or X of T or whatever. You can provide a sample time. I recommend use the same sample time as you did for this input file. Do not do decimation. Decimation means throwing away out of every, if you say 5, out of every 5 data, one of them is going to go to the trash can. So it is going to pick only a subsample of your data set. Okay, so unless you really want to kill some of your data and only keep some of them, do not use decimation. In the save format, you can do time series or array. I would go with array. And here, if you see, I have this Excel file I made, and in cell number A2, I have the frequency value of 5. So it is going to read that 5, and then it is going to write for me sine of 5t in a mat file called results.mat. Okay, so it is done. Right, and now you see here I have result.mat. That is the file that has that sign in it. So let's go ahead and check it. So this is that file, and I'm gonna load it, see what's inside it. So here I say load and then result.mat. And it does, and you clearly can see X, and let's plot it. So plot X column 1, which is time values, versus X column 2, which are the actual sine function values. And something is going on here. Okay, it's 2 by 1001. I see. The rows are big, not the columns. So I have to say row 1 and all columns, and then row 2 and all columns. Okay, that's what I need. Okay, and you clearly see this is a sine function, and if you measure the frequency using this cursor, right? So if you can find 2 points that are corresponding to each other, if you click here, for example, you see that the number is almost the X, which is the time here, is 0.63. And then I'll try to click on the next corresponding point. So I need another data cursor. So I hold down Alt and click to get one more of that. Because if you don't, it is going to clean this up and put that data cursor here. And now I've tried to move this guy and put it as close as possible to 0. So it's somewhere between these two numbers, 188 and 189, and this is 0.63. If you subtract these two numbers, you see the subtraction is about 1.25. Okay, so the period here is about 1.25 seconds. And then 2 times pi divided by t is going to be your omega. And you see it's what? It is 5 radians per second, which I specified. So everything clearly matches and everything is working just fine. So this is file IO, reading and writing from and to files, which I showed you here. And let me show you a few more things. and then we can move to other demos. So I have a demo number 3 that I'll show you, but what I want to show you is one or two more elements of dashboard that make life a lot more pleasant looking. I mean, like, they make your Simulink a lot fancier. So let's say here I have a mechanism for turning something on and off, correct? And let's say I need a time block, so I can get it directly from clock or from the ramp function. And then I need a switch block, which is under signal routing. And then I need a constant block. And then I go under dashboard, and here I bring in a light or lamp, and I would also bring a toggle switch. So the goal is this: I send the time to the switch, and I want the time to be bigger than 5 seconds for the switch to activate. Okay, and as long as the time is not bigger than 5, I do not want anything to happen, so it should be just 0. But when time is bigger than 5, if the user allows the system to turn on, then I say, okay, fine, turn it on, right? And then send the result of that to a scope block. Okay, so here it means don't turn the device on before 5 seconds. After 5 seconds, if this guy is 1, which means I'm allowing it to turn on, then turn it on. Okay, now to make that visually better, I would relate this block to this toggle. So using this toggle button, I can change the number constant here from 0 to 1 or 1 to 0. And to show that the device here is turning on, I connect it to a light. So let's say before 5 seconds, don't turn the light on. After that, let me click on the switch to turn it on, right? So here, I double click on this light and say I want this signal. Okay, and it says what kind of color do you want for the light, and I say turn it red, let's say. Okay, and I do that. And then, so when it turns on, it's going to be red. And then it says, what is this toggle is going to do? And I say, I want this guy. I want this, that when I say on, it's 1. When I say it's off, it's 0. Okay, so now let's do it. So you see, I did not turn it on. It was, or let's see. Well, it is on, I guess. Seems like it is on. Let me double check. There we go. So right now it's off, which makes this guy 0. If I click, makes this one 1. So you see clearly I can change that. And this light, I guess I got it disconnected. Connected to that, the state is 0. Okay, now here we go. Now it's interesting. Look, when this one is off, what happens? This is 0, that is 0, so this one is 0. And remember here it says a state 0. It means when the state is 0, turn it on, right? I can say no, when the state is 1, turn it on. Okay, and when the state is 0, turn it off. So here, now I do the opposite. Look, right? Nothing. And now if I turn this guy on and do it, there we go. And you see, it wasn't on all the way. It was on from after 5 seconds. If I want, I can go here. And now you clearly see the switch is on, but it doesn't turn on because I don't want anything to happen until 5 seconds. So you see, I'm stepping forward, nothing happens until I get to the 5 seconds. When I get to the 5 seconds, then yes, I can turn it on. And to make this go a little bit faster, I first activate this and I say each time go, let's say 50 steps forward. So now here, let's see. Okay, I guess it was too many steps that I set up already. Let's make it just one step. One, good. Here we go. You see, in the beginning it's off, and then I need to move enough steps forward to get to the 5 seconds. There we go. You see, it moved to the 5 seconds, it turned on, and it stays on until what? Until the end of simulation. But if I turn this off, it doesn't matter how much I wait because I turned the switch off. Okay, so using these dashboard elements, you can make your simulation a lot more graphically pleasant. Let me show you a few more things, and then we can go to more advanced topics. So here, I would go, you see here, that's the simulation. And yes, you have debugging, you have modeling, and format and everything. I want you to go under format, and here you can do a little bit, again, fancier stuff. So you can change the color of the background, foreground, and so on. So if you want to change the color of background, you go here, and let's say I want the background to be green. And then any of these elements, if you want, you can change their color as well. Let's say I want to change the color of this time. So I click on it. It's a foreground element. And I can add shadow to it if I want. I can change the color of it if I want, right? The signal, of course, coming from it. If I want, I can put an image. I can fill up the name, right? Auto name it and so on. As I said, I can add an image to it. So I just need to go and look for some image. And then it's going to put that image as the front image for this block. Okay, so let's say here I go and say time and go to images, and let's put some nice picture. Let's say this guy. So I save the image as, and I call it clock. Save it under downloads, ping image. So now if I go back here and I click on this guy and say add an image to it and look for that ping image clock, now it should add it for me to this block. Okay, so again, you can do a lot of things to make your blocks a lot nicer. If you want to change the font, you can just click on that and then change the font size, okay, to make it better, change the shape of the font and everything. And one of the nice thing this part of format has is this guy, auto arrange. So sometimes you wire the blocks and it's quite clumsy job. I mean, like, there are wires all over the place, blocks all over the place, and they don't look too nice. It's hard to follow the wires, see where they are going. One of the things you can do is allow Simulink to arrange it. Now, it doesn't mean it can do really magic, but it tries to make it a little bit more arranged for you. So here you see it was good enough. It did not need to change anything. It thinks that I did relatively good job, but sometimes these blocks are just too crazy and everything is all over the place. So let's see. Here we go, right? I did mess it up, and then I asked to auto arrange it, and it arranged it and made it a lot better for me. And there are other things too here. One of them is the sample time, okay, which can show you. And then you have this fit to view. You have this zoom and so on. You can take snapshots and so many things, but we'll talk about this later. I just wanted to tell you about this. And let me talk about one more thing that might be useful to you, and that is under modeling. This is this model setting. If you go here, here are some settings that might be really useful to you, especially under solver. Here you can change the start and stop time, but more important than that is the solver solution. Do you want the solver to use variable steps or fixed steps? Typically MATLAB is trying to use variable steps. So when let's say if it's solving for a differential equation, when the functions on the differential equation are changing very fast with time, it is using small steps. When they are rather smooth and slow changing, it is using bigger steps. This way it can solve anything in a shorter time. Fixed step means don't care about how the system is changing. You move forward from one point to the next in a fixed amount of step, a fixed increment. Okay, so fixed steps are typically slower than variable steps, but they are more predictable. But again, I recommend, unless you really know what you're doing, do not change it. And the type of solver here, there are different types of ODE solvers that MATLAB has. Like ODE45 is something it uses for most of differential equations that are called non-stiff. If the equations, the boundary conditions are quite stiff, which means they change all of a sudden and they are not normal behaving functions, then instead of ODE45 you have to change it to ODE15 or 23 and so on. If you wanted to go a little bit fast, you can go ODE113. So you can look at different types of solvers in MATLAB. And more important than that is solver details. So because this is a numerical solution, it has a criteria for convergence and stopping the numerical solver. And here one of them is relative tolerance. The smaller you make this number, the more it takes for the solver to converge and stop, but the numbers you will get are way more accurate. The other thing is, instead of letting MATLAB detect, because MATLAB can change the size of the steps, right? Remember, here is variable steps, so MATLAB will decide how big it will go. But if you want, you can tell it, hey, you can change it, but I don't ever want you to go more than step size of 0.01. I never want you to use a step size of 1 and decide it on your own. I never want you to use any increment more than this, and I want you to use a tolerance for conversion of 10 to the negative 5, 10 to the negative 6. If you do that, it takes a little bit more time for Simulink to converge, but the solutions are going to be way more accurate, okay? And this is really going to help you for the third problem of the second bonus project. Okay, that kinetic energy problem and the car hitting into barriers. If you really want to see the velocity of the car converge to 0 and when s goes to 18 feet, you need to bring these numbers down to see that happening. Okay, so this tolerance, zero crossing, and other stuff are important things. And data import output, I showed you this single simulation output. If you want, you can turn it off. And there are so many other things that you can write from Simulink to the workspace. You can write timeouts, the output state, anything, right? You can go to diagnostics and stuff and change when something arises. Do you want Simulink to throw an error at you, or just give you a warning, or sometimes do nothing? Okay, so how do you want Simulink to handle possible problems? Okay, so there are so many things here, but again, if you don't know, please don't touch them unless you really have a good amount